So very exciting times. We have new TMUA papers to do, written by this person, Jacqueline Tyler, who has a tutoring business. I've put her email in the description below. She's written 4 papers, 2 paper 1s and 2 paper 2s. So this is the first of the paper 1s. We'll go straight into it. It is a nice integration problem. Looks very standard for a TMUA question 1. First, we have to say x. Root x is, of course, x times root x, which is x times x to the power half, or x to the 1 times x to the power half. Add the powers, and you get this. Then we can start breaking the fraction in half to do this minus this bit. Then we can take away the powers. Power 0, take away this, and then 2, take away 3/2 gives us this. And then we can finally, I guess, start integrating. So we integrate. We just put the numbers in at this point. You can convert these back to roots if it makes it easier for you to put the numbers in. It's completely up to you at this point how you do this, though. Here I just did the whole numbers first. So -2 minus -4 is 2, and then did the fractional bit second. And yeah, that ends up being -8/3. So a nice first question. The kind of question you just want to get right without making a mistake on. The volume is, of course, this times that. So that would be that. The surface area is one copy of each of the combinations. So like one side will be this times this, or one face, I should say. Another face will be this times this, and another face will be that times that. And you just need to times that by 2, because it's a cuboid, all the faces are going to appear twice. And now we're told that the volume is twice the surface area. So if we times the surface area by another 2, we'll end up with the volume. We can divide everything by x squared here, because x isn't 0. And then, of course, we can eventually try sorting out some of this. It's a bit annoying, but cancel some more 2's. This makes 3√2 here, which is very nice. Expand the 2 out, and then divide by √2. And then you can rationalize this to get 4√2/2, which is 2√2. And so the answer is B. Question 3, we're going to differentiate. We should probably expand this out first. So very similar to the first question, we just need to make it into a form that we can do calculus on. So change this power, then divide each term separately to make this. So that's going to be this over this, this, to make those 3 terms. And then we can differentiate, of course, which gives us this. When we're substituting in 1, it's super easy because all of the x's just go away, because 1 to the power anything is just 1. And then, of course, this cancels with this, and you end up with 7/4 as your answer. So another question that we just don't want to make a mistake on, right? We know how to do it, we just don't want to make a mistake. Times everything by √a here, and you end up with this. And then times it by √a again, and you end up with this. I'm going to rearrange this to look like that. And now if we make a substitution here of like u equals a to the power half, we can turn this into a cubic equation. And now I stared at this for a little bit until I worked out that 2 is a solution to it. So that means u minus 2 is a factor. And then I just started doing some comparing to work out what the other thing needs to be. So u times 2u squared makes 2u cubed, -2 times -3 makes -6. And then aim for the 9u squared term, so that's going to be -4u squareds here, so we need another -5u squareds to come out there. This actually also factorizes to make this, and so you've got 3 answers in u, which are 2, 3, and -1/2. Now, u is the square root of a, which cannot be a negative number, so we'll get rid of this answer here at this point. And then we can square everything to get 4 and 9, and then we can add the solutions up to get the answer of 13. Question 5. So first, we need to work out the gradient of this line by just rearranging. It's -2/3, and we therefore want the gradient between these 2 points to be -2/3. So y1 minus y2 over x1 minus x2, or however you put it, that needs to be equal to -2/3. So I did this minus this over this minus this. Make sure that goes in brackets because there's going to be a +1 coming out of that, which is important. And then just cross multiply, it solves really easily, and you get p is 5. Next one, this typing shouldn't have come straight away, but that's okay. If Anna is traveling towards Ben at this speed, and Ben is traveling towards Anna at that speed, you can just pretend that Anna is constant, and Ben is going 25 miles an hour faster. So we can just pretend that Anna is standing on one end of this, and Ben is traveling towards her at 90 miles an hour. We can just pretend that. And now, if he's going at 90 miles an hour in our pretend world, and Anna is just stationary, then in 90 minutes, well, that's 1.5 hours. 90 times 1.5 is 135. He'll be 135 miles away. And that's all we really need to say there. This question here, so A1 is 1 plus 1 over 1 plus 3, which is 2 over 4. A2 is 2 plus 1 over 2 plus 3, and so on. You can do this for a bunch of them until you get to A40. And now, okay, well, we just need to multiply all of these fractions together. But what's nice is that this 4 will cancel with this 4, this 5 with this 5, this 6 with this 6, this 7 with the 7, all the way to the end, where the 41 will cancel with the 41 that came a couple of times before. The only things that don't cancel are this 2, this 3, the 42, and the 43. 2 over 42 is 121, 3 over 21 is 1/7, and so it's whatever that is, which I think the only reasonable answer, since 7 times 40 is 280, is going to be this one here. And I think that will be the answer. For this next question, let's get some drawings out. So this is just so y equals mod x is just a V shape in the middle. So y equals mod x minus 1 is just that moved 1 to the right. So that's going to be that. These gradients are 1 and minus 1, by the way, which is important in a second. And this one here is just the V shape kind of flipped over, so this way up, and then moved up by 3. So flipped over here and then moved up by 3, so it ends up looking like this. And now this actually, the question is asking for this area here. But this is actually a parallelogram. My drawing's not amazing, but we know it's a parallelogram because, like I said, this gradient is 1, this is 1, and this is, sorry, minus 1. And this is 1, and this is minus 1, or the other way around. No, that way around. Minus 1 and 1. Anyway, all the gradients are just 1 and minus 1. So this is definitely a parallelogram. So if I could just work out some coordinates, I could just do base times height. So this is 1, 0. This is 0, 3, just because of the transformations. This coordinate, a little bit harder to work out, but we just take the positive bit of the x minus 1 bit, so that's just x minus 1, and the negative gradient bit of this, that's going to be 3 minus x. And we just set them each to that and solve. That makes x equals 2, which means, of course, that y is also 2. Sorry, that y is 1. 2 minus 1 is 1. And so, yeah, all we have to do now is say, well, what's the distance? You know, how long is this line here? Well, it's just 1 squared plus 1 squared square rooted, which is root 2. And this one here is just 2 squared plus 2 squared square rooted, which is 2 root 2. And then times these two things together, and we'll end up with an area of 4 for our parallelogram. Next one here, I decided to factorize out the minus, and then I started completing the square. I just don't like completing the square with a minus in front of the thing. It just annoys me. Take out a factor from the x's and from the y's, and then just complete the square on the inside bracket bits. It creates a lot of brackets, but that's okay. And then we can expand everything out and leave this. And now we think about what the maximum value of this is. Well, the best I can do is make this as 0 and this as 0, and we just get minus 9. If I make these things anything else, because they're always going to be positive, that makes more of a negative number when you do minus that thing. So actually the biggest I can make this is just that minus 9. Anything else is going to be like minus 10 or minus 11 or so on. The biggest I can make that is minus 9. A circle is drawn inside a regular hexagon just like this. Let's just call the hexagon side length 1, because the really nice property of hexagons is they're just full of equilateral triangles, because the angle here is 120, so when you halve it, it's 60, 60, 60. So this is also going to be 1, and this is going to be 1. Let's draw a line up to here, which is for 2 reasons. Partly because I can say this is a half and then do some Pythagoras to work this line out, which is obviously going to be really helpful, but also it's going to be helpful because that's the radius of the circle. So now I have everything I need. The area of the hexagon is just 1, 2, 3, 4, 5, 6 of these triangles. So that's 6 times a half times 1 times root 3 over 2, which turns out to be that. And the area of the circle is just pi times this thing squared, which is that. And then, so therefore, the amount covered is just this over this. Now, to do this, this 4 comes down here, and this 2 jumps way up to the top. So this makes 6 pi over 12 root 3. Of course, that's just half down to that. And then we can rationalize this, and we'll end up with this if we do. And the answer will be B. This is a really cool question. I really like this. So we have the cos graph between 0 and pi over 2, which is roughly here. So that's the cos graph. So we've got this area here to look at. Now, when we square the cos graph, because the cos graph is always between 0 and 1, squaring a value between 0 and 1 lowers it down. Like the square of 0.8 is like 0.64, right? So it pushes it down, thus reducing the area. So this area is definitely less than this one. So we'll get rid of that as an option. In the exact opposite way, though, now the sine graph, the integral of the sine graph between 0 and pi over 2 is going to be the same as the cos graph. It's just the same picture, just kind of flipped over, going the other way. But when you square root a value between 0 and 1, it actually gets taller. Like I just said, the square root of 0.64 is 0.8. So this is actually going to be a taller graph than this, and therefore have a bigger area, so we'll get rid of this. This we can get rid of for the same reason we got rid of this. When you raise something to the power 4, it gets much smaller between 0 and 1. And then this one here we need to think about is actually just a straight line, because it's just got a gradient here of 2 over pi. It starts at 1 when x is 0, and it finishes at 0 when x is pi over 2. So this is just a straight line going from 1 to pi over 2. But of course, since this isn't a straight line, since this one is like a nice tall curve, it's going to have more area than just the straight line connecting the same two places. So therefore, this is going to have the biggest area of the 5. Just a really lovely question, I thought. Really, really nice. f of x is a quadratic function, passes through this, has a turning point in this. So this question is very, very easy if you know what to do. You just set up the square version. So this quadratic has a turning point at -1, 3. You just have to shove the a here, because that a is independent of the turning point. It just stretches the graph. It makes it kind of skinnier to flatter. It stretches it vertically, so it doesn't make a difference to the turning point. And now, of course, just to find a, we just put the coordinate they've told us in, and we just solve for a, and it's super easy. and then you put a back in, and then you work out which one of these things that expands to, which is going to be this one. And yeah, that's question that done. If you've watched my video on multinomial expansion, you'll find this question very easy. To find this term, we need 3x's. We only need one of the y squareds. I should have put y squareds here, but we only need one of the y squareds. And we need 1 because you must take 5 things. And then the answer is just 5 factorial over 3 factorial, 1 factorial, 1 factorial, which is just 5 times 4, which is 20. So yeah, watch my video on that if you'd like to know how to do questions like that very fast. For this thing multiplied by this thing to be bigger or equal to 0, you either just need this thing to be bigger or equal to 0 and that thing to be bigger or equal to 0, or this thing to be less than or equal to 0 and that thing to be less than or equal to 0. Now the thing is, between pi and 2 pi, the sign graph is never positive because it goes positive to pi and then is negative from pi to 2 pi. So we can't have this in this range, and therefore it doesn't matter whether we can have this. This is just not going to happen because we need both anyway. So it turns out we want both to be negative. This one is always negative in this range, so we just need this one to be negative 2. Let's rearrange it a little bit, and we end up with this. Draw the cos graph if you need to. We're in this section over here between pi and 2 pi, and we want cos to equal root 3 over 2, which is the highest value up here. That's pi over 6 back from 2 pi. So we'll just take away pi over 6. We'll get 11 pi over 6. And for that to be bigger than the root 3 over 2, we just need to be in this little section here between 11 pi over 6 and 2 pi. And that'll be our answer there. 15 then. This is a really weird question, which I didn't really know what to do with. But if you just evaluate f of n as best you can, it turns out to be actually a really easy question after that. You just need to be brave enough to evaluate this. So yeah, just integrate it. Shove in the n and cancel out an n, and 1 take away 3/4 is a quarter, and you just get f of n is a quarter n, which you can then just put into here as f of r, so a quarter r, and then the question ends up being not too bad because you bring the quarter out. You should know the result for the sum of r. It's just up to n is just n into n plus 1 over 2. The quarter just sitting outside, and then we need that to be less than 69 after some cancelling down. Quite a fancy way to finish this off. 69 is 23 times 3, times the 3 by 8 to get 23 times 24. And clearly we need n to be less than 23 as a whole number to make this work. So 22 will be the one that will get it done. And yeah, quite a cool question actually in the end. Graph of log to base 10 of x is translated negatively by 2 units in the y direction. So that's just log to base 10 of x minus 2. But of course we can intelligently write 2 as log to base 10 of 100. And then combine these logs together, and now we can see we've gone from f of x to f of x over 100. So that's a scale factor of 100 horizontally. And that question is done too. This is a nice question. A very similar question was asked a few years ago in the TMUA paper. If you've got a set of data with 10 pieces with a mean maybe of x bar, then that means the total for that set is 10x bar, right? You just times the number of pieces of data by the mean to find the total in that data set. Same thing for the second data set, except you know the mean is 4 more than the mean for the first. So that's going to be 20 times x bar plus 4. So the total of the second data set is 20 pieces of data times its mean, which is x plus 4, as it says. Sorry, x bar plus 4. Now, after you do some exchanging, of course, if you move one piece of data into the first and then a different piece into the second from the first, then they still have 10 pieces and 20 pieces, right? So now we can say, well, the total of the first set of data is now 10 still, times some other mean, let's just call it y bar, and the total of the second is still 20 times y bar plus 1, because it's only 1 more now. And now the trick we can play here is that these totals must be the same in the initial instance as in the last instance. So basically this plus this must equal this plus this, because you haven't changed any data, you've just put one into one box and moved another into the other box. So the total should still be the same. So we can say this plus this must still equal this plus this. If you do some rearranging, you get this, divide by 13, you get this. So the new mean of the first, remember y bar is the mean of the first data set at the end, that's 2 more than it was at the start. So the answer is 2 here, and that will be the answer. Question 18, again, a very similar question asked in some previous, I think TMUA and Matt asked this in the same year, if I remember correctly. Or maybe it was one did it 1 year after and copied the other, I can't remember. But anyway, what we're going to do is we're going to write this out until cos squared of 44. And now instead of writing cos squared of 46, I'm going to say 1 minus sine squared of 46. And then I'm just going to keep doing that all the way up to 90. The reason I'm going to do that is because now I can collect out all the ones. Now, how many ones are there here? Well, I think there's 23 if I count really carefully. I think there are 23 of them. There's a couple of ways you can get that, I guess. You've got the same number of terms before and after. And you're counting from 0. So it feels like, so here I think you've got 22 of them, but then you've got an extra one because it's 23, and then the same number of terms here. So I think that's how I got to 23. Anyway, and then you just take away all the signs afterwards. Now the trick here is that cos of 90 minus theta is always the same as sine of theta. So for example, if theta was 90, you'd get cos of 0 equals sine of 90. Of course, you can square both sides, and that's still true. But what I'm saying is cos squared of 0 minus sine squared of 90 are just going to cancel each other out. And likewise, cos squared of 2 and sine squared of 88, because if theta was just 88, then that gives you cos of 2 equals sine of 88. So all of these cancel out, and you're just left with the 23 in the middle. And that will be the answer. 19 is a great question. I've never actually seen a question like this. I thought it was really good. We've got y equals x as the straight line. Obviously, we've got y equals root x as this curve. Now, apparently, we can draw a line y equals c horizontally across this that breaks this area into 2 equal pieces. So for some value c, and it's just asking us what is that value. Well, it's not asking what the value of c is. It's asking which equation does it satisfy. So okay, the first thing we might want to do is find this area. So then, of course, we can halve it. Now, this point is obviously 1, 1. That's where these two graphs meet. So we're going to integrate this one between 0 and 1, and then take away the integral of this between 0 and 1. So we're going to integrate the curve between 0 and 1, that gives us all this, and then take away the integral between the line. Now, the line, of course, we don't need to integrate. It's just a triangle, so it's a half times 1 times 1. The curve we do need to integrate. It integrates like this. We put the numbers in. It becomes not too bad, and we get the answer of a sixth. So this whole area here is a sixth. So therefore, I need both of these areas to be a 12th. So let's just point at this one here and call it area 12th. And now, can we find some other way to describe this area, which we can then set equal to a 12th in terms of c, which will then lead to one of these answers here? Well, there's a few ways to do it, I think. What I decided to do was I said, well, okay, this point here is CC, because it's on the line y equals x, and y is c, so x is c as well. This point here, y is c, so therefore x is c squared, I think, because then root c squared is c. So that's the point c squared c. What I'm going to do is I'm going to integrate the curve between 0 and c squared. That gives me this area here. Then I'm going to add a rectangle, this whole rectangle here. And then I'm going to take away all of this triangle. And I think that's going to give me this area here, which I'll set equal to a 12th. So one more time. Integrate the curve between c squared and 0. That will give me this area here. Add the rectangle all the way out to there, which will give me the whole area underneath here. Take away the triangle, and we will end up with the area of a 12th. So integrate the curve between 0 and c squared. This rectangle is c is its height, times c minus c squared is its width. Should have closed another bracket there, but whatever. And then this triangle is just a half times c, which is nice and obvious. That should equal a 12th. This looks like it should give me an equation in terms of c. Integrate this. We actually already did this integral, right? It just ends up being this, put in c squared, and you just end up with this here. So that's all fine. And then this is just c squared minus c cubed, and this is just a half c squared, and that equals a 12th. And we're very close to the answer here. All we need to do is collect together the c squareds and the c cubes. That gives us this, times everything by 12, and move that spare one over to the other side. And that's the same as this answer, as long as you times it by minus 1. So therefore, it will be D. And the last question here, I actually cheated on this question, I think. I don't think I did it in the correct way, but it got me the answer, and that's all that matters. I decided to draw this curve. Now, if you factorize an x cubed out, you can realize that it has one like proper going through it solution at x equals 1. And then because it's an upside down quadratic, that means it must have an inflection point at x equals 0, and it looks a bit like this. Then I thought, well, okay, so this is 0 and this is 1. It's an upside down quartic, so it must do this kind of thing. Then I thought, well, okay, the only way to draw a tangent that's tangent at a line that's tangent at 2 points looks to be like this one here. So I think it definitely has a positive positive y-intercept and a positive gradient. So that removes, well, it removes the negative y-intercept. So it's between A and C. And then I just decided that the y-intercept has to be lower than the maximal point of this curve. Now, I don't know that neither of these are going to break that rule, but I thought it would be really quick for me to check. And if it does, then I'd get to the answer straight away. So let's just differentiate this and then set it to 0. And if you do that, you'll get x is either 0, as we already know, or x is 3/4. So that's this point here. Put x equals 3/4 into into this thing here, and after a bit of jiggery pokery, this ends up being this ends up being 3 to the 3 brackets 4 minus 3, which is just 3 to the 3, which is 27. And this is 2 to the power 8. We get this. Now, that is just less, bit of estimation required. What is this? Is this just less than a tenth, or is it just more than a tenth? In either way, I think it is less than an eighth, because it's very close to a tenth. So I think it must be less than an eighth. So C has a y-intercept that's slightly higher than the maximal point of the curve. So I think it can't be C, and I think the answer must be A. Maybe one day I'll go back to this and do this properly, but I really couldn't be bothered at this point. So I just did it that way. Thank you so much for watching, and thank you to Jacqueline Tyler for making that paper. If you would like to have her tutor you, her email is down below.